In this section, this will be the last section in the unit before we work through a series of AP free response problems. We're going to discuss Le Chatelier's principle. Here's what Le Chatelier's principle says, written by the work of Henri Louis Le Chatelier. If a system at equilibrium is disturbed by what? A change in temperature, pressure, or a change in concentration of one of its components, the system will shift its equilibrium position so as to counteract the effect of the disturbance. So if I have a system at equilibrium and I stress that equilibrium in some way by changing the temperature, pressure, or one of the concentrations, then the system has to change and adapt to restore itself back to equilibrium in order to counteract that disturbance or that stressor. That's what Le Chatelier's principle says. This principle states that if a system's equilibrium is disturbed, the system will react so as to reduce the impact of that disturbance. With concentrations of reactants or products, the interpretation of this is clear. If the amount of reactants is increased, the equilibrium will shift using the additional reactants to produce more products. This reduces the amount of the added reactants, thus reducing their addition. If the amount of products is increased, the equilibrium will shift using the additional products to produce more reactants. This is reducing the amount of added products, thus reducing their addition. Let's first take a look at change in reactant concentrations. Changing the concentrations of reactants or products disturbs a system. It creates a stress. In response to that stress, the system will shift to a new equilibrium position. Increasing the concentration of either reactant, in this case, causes the reaction to consume some of those added reactants, reducing the amount of their increase while creating more products. So if I increase the concentration of either reactant A or reactant B, the equilibrium will shift towards the products. So we'll consume some of this added reactant to produce more products. We'll consume some of this added reactant to produce more product. Decreasing the concentration of either reactant causes the reaction to produce more reactants, replacing some of those which were lost. So we're always trying to undo whatever the change or the stress was, or use up what was added or put back what was taken away. So if we remove some of reactant A or some of reactant B, we're going to shift our equilibrium toward the left to produce more reactants. In doing so, we will consume some of the product. Change in product concentrations. The same principle holds for a change in product concentrations. The system will react so as to reduce the extent of the change. Increasing the concentration of either product, if I increase product C or product D, causes the reaction to consume some of those added products, reducing the amount of their increase while creating more reactants. So we'll consume some of this product and shift our equilibrium toward the left and create more reactants. Same occurs if I increase the concentration of D. I use up some of it and shift the equilibrium back towards the products and create more products. Decreasing the concentration of either product causes the reaction to produce more products, replacing some of those which were lost while consuming some reactants. So if I lower the concentration of C or lower the concentration of D, the equilibrium will shift to the right in order to replace those products that were decreased, and in doing so, we have to use up some of the reactants. Temperature change. To understand the impact of a change of temperature, think of the heat absorbed or released from a reaction as a reactant or product. Then just apply Le Chatelier's principle to heat as you would for any other reactant or product. For an exothermic reaction, consider heat as a product of the reaction. Then consider an increase of temperature as an increase of products, which will drive the reaction toward the reactants. For an endothermic reaction, consider heat as a reactant. Then, an increase of temperature is an increase of reactants, which will drive the reaction toward the products. Here's a closer look at exothermic reactions. For an exothermic reaction which releases heat to its surroundings, rewrite the equation with heat Q as a product, which we see here. Then, an increase of temperature is the same as adding more product, so the reaction will move or shift toward the reactants to consume that addition of heat. A decrease in temperature is the same as reducing a product, so the reaction will proceed toward the products in order to counteract that decrease in temperature. Endothermic reactions. For an endothermic reaction which absorbs heat from its surroundings, rewrite the equation with heat Q as a reactant. Then, an increase in temperature is the same as adding more of a reactant. If we have excess reactant, we've got to use it up, so the reaction will move toward the products. Equilibrium will shift towards the products. A decrease in temperature is the same as reducing a reactant, Q. So we've got to shift our equilibrium to make more reactants to put back that amount that was decreased. Pressure changes. Applying Le Chatelier's principle to a change of pressure is a little less obvious, since pressure is not a reactant or a product. However, a reaction in a sealed container will result in a change of pressure if there are a different number of moles of gas on the products or reactants side. If there are more moles of gas, there will be more pressure. Then, the principle would indicate that an external change in pressure will result in the reaction proceeding so as to reduce the extent of that change. For example, in this reaction, the reactant side has 4 moles, 3 of H2, 1 of N2, and the product side has 2 moles of NH3. As the reaction proceeds from the reactant side to the product side, the result will be a decrease of pressure because there are fewer moles on the product side. If the external pressure on the system increases, so if I increase the pressure of the system, the reaction will move toward the product side to reduce the extent of that external change. So if the pressure is increased, the reaction will move toward the side with fewer moles in order to combat or decrease that increase. A reduction in pressure, if I lower the pressure externally, the reaction will move toward the side with more moles in order to increase the pressure to counteract that decrease. So, if the external pressure under which this reaction is taking place is increased, the reaction will proceed toward the products, toward the side with fewer moles, to reduce the pressure. If the external pressure under which this reaction is taking place is decreased, the reaction will proceed toward the reactants, the side with more moles, to increase the pressure. This effect only occurs because the number of moles of gas is different on the two sides of the equation. If they were equal, if both sides had equal number of moles, a change in pressure would not shift the reaction in either direction. That's an important note. So this only happens because we have differing number of moles of gas on either side of the reaction. Volume change. A change in the volume of the container in which a reaction is proceeding will result in a change of pressure. A decrease in volume will result in an increase in pressure. An increase in volume will result in a decrease in pressure. In those situations, first determine whether the pressure has been increased or decreased. Then, use what you've learned about how to apply Le Chatelier's principle to a change in pressure, which we just discussed previously, in order to solve the problem. Changing the pressure of a reaction by changing the volume disturbs the system. It creates a stress. If there are different numbers of moles of gases on the right and left sides of the equation, the reaction will proceed to change the number of moles of gas to reduce the extent of the external change. In response to the stress, the system will shift to a new equilibrium position. In this case, there are 2 moles of gas reactants and 3 moles of gas products. So the side with more moles is the products, the side with less moles is the reactants. If the volume increases, then the pressure decreases. The impact of a decrease in pressure is to shift the equilibrium toward the side of the reaction with more moles of gas to combat or counteract that decrease in pressure. So we shift in this case toward the products or more moles of gas. If the volume decreases, then the pressure increases. An increase in pressure will shift the equilibrium toward the side of the reaction with fewer number of moles. In this case, that's the left. So we see the equilibrium position shifting toward the reaction, toward the reactants, or toward the left, in order to counteract that increase in pressure. The Haber process. Ammonia, NH3, is produced for agricultural fertilizer and other industrial uses via the Haber process. The synthesis of ammonia from hydrogen, which you see here in blue, and nitrogen, which you see here in red. We will use this process to study Le Chatelier's principle. Kc for this reaction at room temperature, 25 degrees C, is 6.0 times 10 to the minus 2. That's a K value that's less than 1. We talked in a previous section that values of K that are less than 1 are reactant favored. So this reaction favors the reactants, not the products. So on its own at room temperature, this reaction is not favorable. What can be done to make more products? What can we change? What can we shift to make more products? The temperature can be changed because the only way to change Kc is to change the temperature. This is an exothermic reaction. So that means that heat is a product. In order to shift Kc toward the product, the temperature would have to be lowered. Lowering the temperature will decrease the reaction rate, though, which is not acceptable in industry. Another possible solution is to increase the concentration of the reactants. So I have an initial equilibrium, H2, NH3, N2. At this time, I add more reactant. I add N2. By adding more reactant, remember if we increase the concentration of the reactant, we shift the equilibrium toward the product to consume some of that excess or additional reactant. Reaction shifts towards the product. So look what happens. We consume some of that N2. We consume some H2, but we also increase the production of our NH3. And then eventually a new equilibrium is reestablished, and we can see that more product will be produced. An industrial solution, one of the things that happens in industry, is to remove the product as it is formed. By removing NH3 periodically and continually adding more reactants, the reaction forms even more product. So we're doing two things at the same time, right? We're both increasing the reactant and decreasing the product, continuously driving that reaction towards the production of product. The catalyst that you see here does not change the Kc, it doesn't change the equilibrium constant. It just works to speed up the reaction, okay, happen at a faster rate in the industry. And so what we do is we open a valve here to remove some product. And we know that if we decrease the concentration of a product, we then shift the reaction towards the creation of more product. Sometimes changing the temperature is the best way to shift a reaction in one direction or the other. In this example, if the temperature of the system is increased, this reaction, it's an endothermic reaction. So the heat, or Q, can be viewed as a reactant. The system should accept or take in the thermal energy supplied to favor the endothermic reaction, and the equilibrium will shift to the right toward the forward reaction. Okay? So if we increase the temperature, if we add energy here in the form of heat, then the equilibrium will shift toward the right, or in the forward direction, toward the production of those products. Here's another example that we can see just by changing the temperature. When the temperature of this reaction is changed, there is a dramatic change in appearance. So you can see delta H is positive here. That means the reaction is endothermic, and that would mean that heat is a reactant. Okay. Many ions containing transition metals, in this case the transition metal is a cobalt metal, produce colored solutions. The cation cobalt hexa aqua ion, cobalt with 6 waters and then 2+, yields a pink solution. Whereas cobalt chloride ion, CoCl4 with a 2- charge, produces a blue solution. So let's look on the next slide what happens when we increase or decrease the temperature. So if heat is a reactant, because it's an endothermic reaction, what happens at high temperature? If we increase the temperature, add heat, we need to use up the excess. When we use up that excess, we're going to produce more product and shift our equilibrium to the right. And so when that happens, this cobalt chloride ion species is favored and the solution will be blue. If we decrease the temperature, or we have low temperature, decrease, remove some heat, right? We're going to shift the equilibrium towards the left in order to put back that heat which was removed. Okay, so if we shift the equilibrium to the left towards the reactants, then the solution will be pink because the cobalt hexa aqua ion species is favored. You can see at high temperature, at 100 degrees Celsius, we have a blue solution. At 25 degrees Celsius, we have a pink solution. If you want, you can click here for an animation of this process as it happens in the lab. Here's another equilibrium application. The reaction that occurs in a car engine is an exothermic process. So you can see I have heat as a product in this combustion reaction. Cooling the engine will shift the reaction to the right. So if I decrease the amount of heat, I'm going to shift the reaction this way to replace or produce more of that heat which was removed. So cooling the engine will shift the reaction to the right, ensuring full conversion of the gasoline to energy and its waste products. So the goal here, we want to make sure we use up all the gasoline, right? We don't want any waste. So we cool the engine to continue the combustion of that gasoline in the forward reaction. Let's talk now about the reaction quotient, Q, and how it relates to the equilibrium constant, K. The reaction quotient is the ratio of products to reactants to the power of their coefficients at any stage other than equilibrium. So it's our equilibrium expression, but not at equilibrium, okay? And so we call that Q the reaction quotient. The value of Q and its relationship to K provides information as to which way a reaction will shift to reach equilibrium. So if Q is greater than K, then there's too many products. This top part of the fraction is too big. Too many products. So the reaction will shift left or toward the reactants to reach equilibrium. If Q is less than K, then we have too many reactants, and the reaction will shift right toward the products to reach equilibrium. If Q is equal to K, that means the reaction is at equilibrium, and then there will be no shift. Example 9, reaction quotient Q and K. Given the following reaction, which way will the reaction shift to reach equilibrium given the following initial concentrations? So we have this reaction of N2 gas plus 3H2 gas produces 2NH3 gas. We're given 3 initial concentrations, and we're given the equilibrium constant K. So our reaction quotient, Q, is written just as we would write the equilibrium constant expression. It's the ratio of the product concentrations to the reactant concentrations. Don't forget to raise each concentration to its coefficient. So this is 0.41 squared divided by 0.41 times 0.41 cubed. All right, so mathematically, this is 1 over 0.41 squared, just for ease of calculation on my part, but you don't have to do that if you don't want to. You can plug this in just as it is. So when I get that, I get 5.95. Okay, so we'll review the answer on the next slide, where we compare this value of Q to this value of K. All right, so given the initial amounts, 0.4 molar, and this value of K, 0.037, the direction the reaction will shift to reach equilibrium can be determined by comparing Q to K. On the previous slide, we calculated Q to be 5.94, but you can see the calculation here again. In this case, Q at 5.94 is greater than K at 0.037. If Q is greater than K, that means we have too many products. Products predominate in that case. And so we need to use up those too many products. How do we do that? By consuming them to create reactants. So the reaction will shift left toward the reactants to reach equilibrium. All right, here's a final application before we solve some questions. Shower scale, like the scummy scale, lime scale stuff that builds up on your shower door and stuff, is typically composed partly of metal carbonate precipitates, which do not readily dissolve in tap water. So these solid precipitates, which has a very small K value, 6 times 10 to the minus 9. So if we use an acidic cleaning agent, we can dissolve that solid, right? What we're trying to do is dissolve the solids, because those solids are stuck on our shower door, right? The way we do that is by using an acidic cleaning agent, which shifts the equilibrium to the right. How? Because the carbonate ions are depleted, they decrease through the reaction of them with the hydrogen ions from the acid. This shift results in the solid scale being dissolved, removing it. So if we decrease this amount of CO3 2 minus, decrease the CO3, we can drive the reaction towards the right, dissolving all of this solid.